to welcome everyone to our next TDS webinar. It's my great pleasure to introduce Professor Hitay Ozbay. And pretty much all the TDS workshops I ever been to, I have seen him, which is always great. So he's a very active member of our community. But I didn't know actually until I received his biography that he served as a faculty for 15 years to our arch enemy in football, which is the Ohio State University.
Yes, I didn't want to insult you with other stuff,
Well, I think that's just a side remark, but indeed, his work on time delay systems has been stretching over many decades now. And today it's our great pleasure to welcome him and listen to his results on strongly stabilizing controllers for time delay systems. So Hitay, the floor is yours.
Well, thank you, Gabor Wim, for the invitation. Today I'm going to talk about strongly stabilizing controllers for systems with time delays. I apologize if you have seen this talk before, because I gave the same talk over the last 12 months, I think, in a couple of different places, including Central, Supelec, Groningen, and a couple of universities in the US. So how do we proceed? Okay, here is the outline of my talk. The first part deals with the problem definition. What is strong stabilization and why is it is a difficult problem? And in the second part, we'll try to extend some of the methods that exist for finite dimensional system strong stabilization to systems with time delays. And I will give some examples and list some open research problems that may interest some of you. Okay, so strong stabilization. Disclaimer, first of all, in the literature, in the control literature, there are, as far as I know, there are at least two different definitions of strong stabilization. Here we deal with the definition that I list here. I will go over this in a minute, but there is another strong stabilization concept which has nothing to do with this one. So you have been warned, okay? So if you expect to see something else, that's not it, okay? Okay, so we are dealing with the feedback system stabilization. P is the plant, H is the sensor, C is the controller design. And we deal with linear time invariant single input, single output systems, but most of the results apply to multi-input, multi-output systems as well. And the definition of strong stabilization is this. Given plant and the sensor, you want to find a stable controller C, which stabilizes the feedback system. And definition of stability is that the transfer function should be in H infinity. So bounded and analytic functions in the right half plane. Okay. First of all, observation. If the plant and the sensor are stable, then zero controller, C equal to 0, stabilizes the feedback system, but this is not an interesting problem. So the problem gets interesting when the plant has right half plane poles. Okay. Okay, so right half plane poles makes the plant unstable, and unstable plants are difficult to control. And how difficult it is, I refer to a great talk by Günther Stein. This is the very first Bode lecture given in the CDCs. And the paper related to this has appeared in August 2003, so I refer to this paper. Okay, so basically Günther Stein says the practical, physical, and sometimes dangerous consequences of control must be respected. and the underlying principles must be clearly and well taught. What is meant by this is basically, if you look at the feedback system, let's say L is the open loop system transfer function, S is the sensitivity function. Bode's integral formulas describe what can be achieved and what is the difficulty, okay? So if the open loop transfer function is stable, then the integral of the logarithm of the sensitivity is 0. If the open loop transfer function has right half plane poles, this integral is greater than 0, okay? So there is some level of difficulty here. And Günterstein says in his paper that closed loop systems with unstable components are only locally stable, okay? So for this reason, remember L contains the controller as well. So we'll try to make L stable. So meaning of the body integrals, I'm sure all of you know this, is that you cannot make the sensitivity less than 1 at all frequencies, so the dirt has to be distributed. So we want to use the stable controllers if possible. Some examples of unstable plants include an unstable aircraft model whose transfer function is in this form. A is the unstable pole, H is the delay, and K is the gain. Okay, another example is the inverted pendulum. And if this pendulum has two links, there is an robotic tooling underactuated system is called Acrobot, is an extension of this one. Okay, another important fact. Aggressive design leads to unstable controllers. Okay, what do I mean by aggressive design? So for example, take sensor to be perfect, H equal to 1. And try to do H infinity mixed sensitivity minimization for a stable plant with time delay H, okay? And divided by A, okay? So this is like normalization of the crossover frequency, okay? And if you select W1 and W2, the weights that multiply sensitivity and complementary sensitivity as such, and if you let K over A large, means that W1 is large, so you want to make the sensitivity as small as possible. So that is aggressive design. So you try to make the sensitivity small. And you don't care much about the complementary sensitivity. Okay, so less emphasis on stability robustness, more emphasis on performance with large K over A. Okay, remember H over A is the effective time delay in the system. So here is the graph of K over A versus ln H over A, okay? And you see that if K over A and H values are below this graph, the optimal controller is stable. If it is higher, optimal controller is unstable. So in other words, if the delay is large and K over A is large, the optimal controller becomes unstable, okay? So that is aggressive design, okay? Why strong stabilization? First reason we have seen from Günterstein's paper. Do not introduce extra right half plane poles in the loop gain. So body integral constraints. Second reason is offline testing of an open loop controller implementation. In other words, you have a controller and you want to test the controller's implementation. Typically in the industry, they give a step response or a chirp signal and look at the output and then try to determine the transfer function of this box, whether it matches the desired or the designed transfer function for testing, okay, offline testing. But if the controller is unstable and it is any bounded signal you give here will be unbounded. So it immediately saturates the transfer the output, and then you cannot estimate the controller's transfer function. The third reason is this. When the plant is stable, so let's say this thing is stable, and you measure the output and then pass it through let's say a network, okay? And the network is unreliable. There is a sensor failure or there's a malicious attack in the network. If you use a stable controller, the feedback system remains stable. But if the controller is aggressive and unstable, under malicious attacks, this system becomes unstable, okay? The fourth reason is simultaneous stabilization of two plants. Let's say P1 and P2, two unstable plants, is equivalent to strong stabilization of an auxiliary plant. Okay, so that's another reason. And finally, it's relatively easy to approximate stable controllers and analyze stability robustness of the feedback system when the controller is stable. Okay, so there are 5 reasons to look at strong stabilization problem. Okay, what are the methods for strong stabilization? The very first thing you need to know about strong stabilization, it's not always possible. So it all depends on the right half plane pole zero locations of the plant. So when I say plant, from now on, I'm talking about the product of plant times sensor, okay? So you can find a strong destabilizing controller if and only if the plant satisfies the parity interlacing property. What does it mean? Between every pair of positive real axis 0, you have even number of poles in the system. So in the left, parity interlacing is satisfied. So there are no poles here between these two zeros. It's even. There are 2 here. It's even. It's okay. Here, the parity interlacing property is not satisfied because between these 2 zeros, you have 1 pole. Okay. So for such a system, strongly stabilizing controller does not exist. The second thing you need to know is that even if the parity interlacing property is satisfied, for example, something like this, the minimal order of the strongly stabilizing controller can get very large. Okay, so in this example, as these zeros get closer to the real axis, the system gets closer to violating the parity interlacing property, and it becomes more and more difficult to find strongly stabilizing controllers, in the sense that strongly stabilizing controller order has to be very large. Okay, so that's another important fact. Okay, so what is the mathematical problem behind strong stabilization? Basically, construction of a unit in H infinity satisfying certain interpolation conditions. Okay, so that's the one-line description of the mathematical problem. And here is the specifics of it. Okay, so let's say plant is factored as n over d. It's a coprime factorization in H infinity. Let's say your controller is Q in H infinity. It is stable. Then this feedback system is stable if and only if U and U inverse are in H infinity. So in other words, U is unit and U is defined by D plus NQ. And U evaluated at the right half plane 0 of the plant should be equal to D evaluated at the right half plane 0 of the same plant, okay? So for all right half plane zeros, including at infinity, z of n of s, u must satisfy this interpolation condition, and u has to be unit in H infinity. And if you can construct such a unit, then your sensitivity function becomes d over u, and your controller becomes u minus d over n. Okay, note that due to interpolation conditions, this thing is in H infinity. And since u is unit, its inverse is in H infinity, so S is also in H infinity. So that's the mathematical problem that defines the storm stabilization. There is a very simple algorithm, old algorithm. I want to go over this very quickly, so please bear with me because it illustrates the difficulty level, okay? Let's say the zeros of the right half plane zeros are z1 through zn. And let's assume they are distinct and the last one is at infinity. And the interpolation conditions are, let's say d of z1 is r1 through rn. Okay, so zi's are given, ri's are given, and you want to construct a unit in H infinity which satisfies these interpolation conditions. Okay. So what you do is you start with a constant. First interpolation condition is satisfied by this constant. U1 is R1. Then at the next step, what you do is you take the previous unit and multiply it by 1 plus a sub k, f sub k to the power L sub k, whereas f sub k is 0 at the previous interpolation points, so that u sub k satisfies the previous interpolation points as well, okay? And then you want to find a sub k and L sub k such that magnitude of a sub k is less than 1, okay? And L sub k is greater than 1 such that these interpolation conditions are satisfied. So by small gain theorem, this becomes an invertible function in H infinity. So it's a unit, okay? So here is an example. Interpolation points, we have 3 of them. There is a 0 at infinity, at 1 and 2, and there are a couple of poles in between them. Okay, so PIP is satisfied, no problem. Okay, so double pole at S equal to P. So these are interpolation points. First one is this one. Second one is this one, R1, times this expression. Now, F2 is S minus 1 over S plus 1. And U2 becomes this. So you want to find an A2 which satisfies this interpolation condition. If you solve for A2, you see that there is a 1 over F2 of Z2, and there is a factor here, which is ratio of R2 over R1 to the power 1 over L2 minus 1. So this, you are looking for the smallest possible L2 so that the order of this thing is as small as possible. But it turns out that for this example, L2, the smallest L2 is 8. Okay. And the next interpolation condition is also satisfied with L3 equal to 1. And finally, you get a 10th order U. And since there are 3 interpolation conditions, there are 3 pole zero cancellations in this expression, and in the reduced version of C, the 7th order controller is this one. Okay, so pole zero locations. So determine how large this quantity is and what will be the smallest L2, so the order that appears in the interpolation, okay? So another interpolation is using infinite dimensional transfer functions. So if you choose the U as an exponential of f of s, such that magnitude of f of s is bounded on the real part, positive, and then the interpolation conditions can be expressed as such this becomes a Lagrange interpolation problem, and you can solve it, okay? So if you do the same example with such same example, apply this idea, you find an f of s, and e to the f of s is u, okay? But in this case, you can see that Bode plots of 1 over u, this red line, is relatively large, okay? And you can approximate it by a 10th order one, that's also large. And the question is, can you put a bound on u and u inverse? Because u inverse is related to the sensitivity function, okay? So in order to put a bound, you want a u magnitude which is bounded away from 0, that is greater than epsilon, and bounded by an upper bound gamma, okay? So you want to find a function which goes from the right half plane to this region in the complex plane, okay? It's a ring, essentially, satisfying the interpolation conditions. So because it's a simply connected domain, you can find a conformal map that maps this region to the unit disk and this region to the unit disk, and then do the Nevanlina peak interpolation for the interpolation points and find the optimal u, okay? But the resulting u is infinite dimensional because this transformation between this region and the disk is an infinite dimensional expression, okay? So there are some examples in these papers cited here. The other thing is robustness analysis. Of course, you may consider a coprime factorization with some perturbations, okay? So W1 and W2 are weights, and delta D, delta N are uncertainties subject to normalization of their infinity norms. And if U is designed for this nominal plant N over D, controller is this, sensitivity is this, and if you look at the characteristic equation of the system, you will see that the perturbed feedback system remains stable if the norm of this transfer function is less than 1, okay? So it means that you want to find a controller, strongly stabilizing controller, which makes this norm less than 1. So that puts an additional requirement. So you want to find, of course, as small as possible, the controller which makes the left-hand side as small as possible. So this is a H infinity control with strongly stabilizing controllers. So as far as I know, this is still an open problem. So open problem meaning that what is the smallest value of the left-hand side of this inequality achievable by strongly stabilizing controllers, okay? There are some upper bounds, okay, some sufficient conditions, and there many papers have been published on this topic, okay? Okay, another approach is this, strong stabilization under sufficient conditions. That is, using the small gain. Here is what we do. We take the transfer coprime factorization N over D again. And let's say D is normalized to have the value at infinity equal to 1. So this is always possible, okay? It's just a normalization. Then choose a stable controller, Q, stable, let's say, okay? And that defines the U that we have worked out before. Take an arbitrary unit in H infinity such that W0 at infinity is also 1. Then W0 times U is unitary if and only if U is unitary, okay? So then Q is in H infinity if and only if this Q1 is also in H infinity. Okay, so there is a one-to-one map between these two. Okay. So I define W0 times D as 1 minus R. Okay, so I define an R as 1 minus W0D. So R is computed, no. So then W0 times U becomes 1 minus R minus NQ1. Okay, so if I can make the infinity norm of this expression less than 1, by finding an appropriate Q1, I found the strongly stabilizing controller. Okay, so that's the whole problem. So this is now the standard one block H infinity problem. You use any favorite technique you want to solve this problem. But of course, whether this problem is solvable or not depends on R and N. And R and N are essentially determined by the right half plane poles and zeros of the plant. Okay. So the other thing is you may want to put a bound on the H infinity norm of the controller. So you don't want a controller whose H infinity norm is very large. Okay. So that bound is imposed on the problem. If you do this, then you get a two-block H infinity control problem. So this is equivalent to mixed sensitivity minimization, and its solution is spectral factorization plus one block H infinity problem. It's a well-known problem. The other thing is, this problem, if it is solvable for some particular rho, okay, here, then it is also solvable for all rho greater than rho 0. So this allows a parametrization of a set of all, a subset of all strongly stabilizing controllers. And there are many other methods of strongly stabilizing controller design. I'm just listing 3 of them here. Okay. Especially in the latest one, this one, you can find a very good literature review. Okay. I don't want to go over, spend too much time on strong stabilization methods for finite dimensional systems, but these interpolation methods and strong stabilization by small gain are 2 main techniques for finding such controls. Okay, let's now move on to the second part of the talk, which is actually the main interest for this audience probably. What do we do for time delay systems? Okay, and then I will give an example and list some open research problems. Okay, so for time delay systems, one of the classical methods of designing controllers is to use Smith predictor. Okay, so if the plant is time delay times a finite dimensional term, what you do is you design an initial controller K for P0, okay? So that leads to the complementary sensitivity function T0. And then you form a feedback around, predictor feedback around this K, and that defines your controller, okay? This technique leads to a overall complementary sensitivity transfer function from R to Y as this expression. Very nice, isn't it? But there are several issues: robustness against plant uncertainty, delay mismatch, and this particular structure is not directly applicable to unstable plants. It needs a modification. So let me just give you a modification. So the class of plants, let's say, contain an uncertainty as well. WM multiplicative uncertainty that defines the plant. And you again, you have a predictor feedback around the nominal controller for P0. And this predictor feedback contains an H of S to be designed, which is also used in the feedback path. And H must be stable and must satisfy these interpolation conditions, and it should satisfy this inequality. So basically, this is a Nevanlinna peak interpolation problem, and it is solvable. We know how to solve this thing. Okay, so again, we are not talking about strong stabilization here. So the question is, under which condition this expression C0 becomes stable? So let's say if I define f as this transfer function, P0 times 1 minus h of s times e to the minus hs, by construction, this transfer function is stable. Even if you start with a k of s that strongly stabilizes P0 times h, the question is this: when is this C0, k over 1 plus kf, stable? So you see, this, for this problem, it is better to start with a k which has the smallest infinity norm. So if you use the small gain method that I mentioned there, there was a parameter rho which bounds the infinity norm of the controller. If you let rho small, and if you can solve this problem, it helps the solution of this problem. But this is, as it is, a difficult problem. Okay. So what works here? With approximations, we can use the interpolation methods and the small gain method that I mentioned for finite dimensional systems. Okay, let's take retarded time delay systems, okay? Quasi-polynomial divided by another quasi-polynomial, okay? For simplicity, it's just one delay. It doesn't matter if you have many other delays as well. Let's say R is the relative degree of the plant, and the numerator has roots in the right half plane alpha 1 through alpha n, and the denominator has roots in the right half plane beta 1 through beta m. Note that I'm considering only finitely many right half plane poles and zeros here. Okay, in this case, you can obtain a factorization of the plant P as such, where there is an m alpha and m beta. Okay, so P0 here, defined by m alpha and m beta like this, is a finite dimensional system. And P1 defined in this manner is infinite dimensional, but it is invertible in H infinity. Okay, remember, invertible in H infinity means unit in H infinity, and in the strong stabilization problem, unit transfer functions do not cause any problems. So if you can find a C0 strongly stabilizing P0, then C0 times P1 inverse also strongly stabilizes P. But, okay, so this is finite dimensional. I know how to solve this problem. In the first part of the talk, I have given you some techniques for it. But now what happens with the P1? Okay, so this P1 inverse, obviously, there are unstable pole-zero cancellations internally in this expression, and it's very difficult to implement it, okay? So one way to deal with this, somehow you are going to approximate it by P1 sub A, an approximation of P1. And you will use this approximation in the controller expression. So this controller strongly stabilizes P if you look at the characteristic equation, if this condition is satisfied. And again, T0 is the complementary sensitivity function, obtained from C0. Okay? And P0. Okay, the finite dimensional expression here. Okay, here is an example. So n is this quasi-polynomial, and d is s plus 1 times d0, which is this quasi-polynomial. And the factorization gives me my P0 here. And I find a C0 strongly stabilizing controller for this plant, which satisfies the parity interlacing property. And I approximate P1 that I obtain, which is infinite dimensional. Look at its magnitude, this blue line, by P1 approximate A. Okay, you see, in the low frequency range, I approximated well enough, and that's sufficient for me, because if I look at the small gain condition, which guarantees feedback system stability for the original plant, this magnitude does not exceed 1. In fact, it is less than 0.2, so there's a lot of room for robustness. So that's the example. So conclusion, if you have a retarded time delay system with finitely many right half plane poles and zeros, no problem. Now, what happens if you have input-output delays? Well, in this case, what I suggest is take the delay, approximate it by a Pade approximation. So now this becomes same form as in the retarded time delay case. Apply the same technique. But this time we have two approximation error terms. One comes from the delay minus its Pade approximation, and the other one comes from this P1A and P1 inverse. So this expression has to be taken care of. So in addition to this, we have another term which involves the approximation error of the delay. I don't want to bore you with this with these details. Instead, I want to give you another example which uses the sufficient conditions, the small gain theorem. So, okay, let's recall what it was. So I do an coprime factorization, inner-outer factorization of the numerator term. Controller expression is this. Okay, and again, I find an outer function W0 such that W0 at infinity is 1. And then I try to find a Q1 which makes this quantity less than 1. Okay, so this this was the approach for the finite dimensional system. But in this case, your N contains M, and M is probably contains a time delay, let's say, okay, pure time delay, for example. So this N will be infinite dimensional in this case. R is not, because if your W0 is rational, then R is 1 minus D, so it's going to be finite dimensional if the plant has finitely many poles in the right half plane, okay? So N is infinite dimensional, R is finite dimensional. Two problems. I'm going to discuss two problems. Just to find a strongly stabilizing controller, and given the plant, a weighting function, and an upper bound rho, find a strongly stabilizing controller such that this sensitivity minimization condition is met. Okay, so these two problems, SS0 and SS1, are going to be discussed with an example. Okay, here is the plant. This time, the example is multi-input, multi-output, just to illustrate that it also works for such systems as well, okay? The factorization is in this form, where M is an inner transfer function, 2 by 2, and 0 is just a first order, 2 by 2, and 1 is this transfer function, but the thing is S minus P divided by this expression is stable. So this expression is stable. Okay, so it's invertible in H infinity. And P is the root of this expression. There is only one root of that in the right half plane. It's approximately this. So I define D as such. Okay, so D is the unstable part of the plant in this D inverse. Okay. So for SS0, I look at D plus M and 0 and 1 C, and C is in H infinity. So N1 is invertible in H infinity, but it's we use a pseudo inverse. And then C becomes N1 pseudo inverse times C1, and this is the pseudo inverse. So how do I compute C1? Okay, C1 gives me this problem. R is D minus I this time. And the SS0 solution exists using this sufficient condition, small gain theorem, if this expression is less than 1, gamma 0. So clearly, this is computable, okay? And the solution depends on H. So if you look at the graph of H versus gamma 0, you see that you can go up to H equal to 0.3377. Up to this value of H, you can find a solution to the SS0 problem. That is strong stabilization only. Okay? But I can use the same idea for SS1. That is bounding the infinity norm of W1 times S for a given W1 and the upper bound rho. Okay? Then I can also transform the problem to another one block H infinity problem. I don't want to bore you with details. And this problem now is solvable for the same example. Okay. If you take rho equal to 2 and W1 equal to this expression, okay, it is solvable only up to H equal to 0.1354. Okay, so if you impose another condition on the weighted sensitivity, how high you can go with the time delay, it goes down. Okay, previously we had 0.33 something, now we go up to 0.1354. Okay, summary. We have seen interpolation methods and a small gain approach, which can be solved by the classical H infinity problems. And these give us strongly stabilizing controllers and some conditions on the sensitivity bound for time delay systems and for finite dimensional systems. But the question is, what is the optimal controller in the H infinity sense? Among the set of all strongly stabilizing controllers, this is an open research problem. Okay, so we used approximations of H infinity functions in order to find finite dimensional controllers, strongly stabilizing. Okay, and this required, for example, here, you see this expression. So the approximation error contributes significantly, may contribute significantly to the error here, okay? So given a fixed order approximation that is desired to be stable and invertible, what is the smallest H infinity norm that you can get for this problem? It's an interesting open research problem as far as I know. And fixed order, low order stable controllers, this is also another subject. Strongly stabilizing controllers from the extended Smith predictor. Remember, there was a K over 1 plus Kf in the Smith predictor expression. Under which conditions it is stable? It's worth investigating. And extension to nonlinear systems is also another open research problem. Okay. Thank you very much for listening. The material that I have presented here is from many publications that I had with my colleagues and former PhD students whose names are listed here. I thank them also. Okay. Any questions?
Well, thank you very much for the very informative talk. And indeed, the floor is open for questions.